we've been talking about solutions, and I kind of tease that there's too many S's in solutions. There's like the, did we do this slide? Okay. There's like, there it is. Solutions, too many S's. Maybe we didn't do this. Maybe just start. Okay. So when I do problems in chemistry, a lot of times I'll draw a picture because it's like, it kind of makes it takes the fear out of it. So we're going to add solute to solvent. And if that solvent is water, then it's going to be an aqueous solution. And when we add those two together, I remember I got this part anyway on Monday. Solute plus solvent is equal to solution. Too many S's. Now, I think I used the reference about making Kool-Aid the other day. So I think it's just 1 cup, not 2 cups. But I probably put in make it half a cup. I like my Kool-Aid kind of tangy. But my daughter would put in like 1.5 cups. So one of the things about it is if this isn't a beaker, say this is your pitcher of water that you're going to go ahead and make Kool-Aid in, if you keep adding sugar, okay, sugar to it, you know that actually at some point, I call this sludge. At some point you're going to get sludge, which is sugar sludge down at the bottom there, right? It can't dissolve. It has a limit. And actually, that limit is what we call the solubility of sugar in water. And the solubility has to do with, the temperature. Okay? Water is one of those things that if we heat it up, I bet we can dissolve more and more. That's how we make candy, right? So solubility is how much of the solute you can dissolve in a solvent. Maybe at a given temperature. Now, this right here that I've drawn, this is an example of a saturated solution. Saturated means that it just, like if you're saturated with homework, it means you can't take any more homework, right? So that's kind of what it is. It means that there's so much sugar particles already dissolved that it can't take any more, so it's just going to make a sludge at the bottom. Okay, that's saturated. Unsaturated would be my sort of Kool-Aid, where I only add 1/2 cup of sugar and it all dissolves. It's unsaturated. Why is it unsaturated? I can add more. Supersaturated is kind of fun. And I'll show you, I got some examples to kind of show you. Anytime in science you run into this word super, you better watch out. So super means that it's above expected. So basically a supersaturated solution, basically you have kind of finessed the solution so that you have more solute in dissolved than really should be. So that's supersaturated. We have supersaturated and super cool. They're kind of fun too. So here we've got, this could be my Kool-Aid, and this could be my daughter's Kool-Aid. A is my Kool-Aid, B is my daughter's Kool-Aid. So, although you don't make Kool-Aid by dissolving sodium chloride in water. But these little piles are our solute. This little beaker right here is our solvent, and we're going to make a solution over there. Now, it's kind of fun. This one right here, this guy right here, kind of reminds me of what's happening when you see a sludge at the bottom. Okay, that's to say that kind of the pile, looks like a pile of dew maybe, but the pile right there is the sludge at the bottom, and the little arrows means it's dissolving. Little arrows out means it's dissolving. Little arrows in means it's, what we say, precipitating or crystallizing. So it's kind of what we call a dynamic process. That's to say that down here, it looks like it's static, but we have some of those particles going into solution and some of these particles coming out of solution. So it's kind of fun. So let's just say if we take 30 grams of sodium chloride, 100 milliliters of water, it all dissolves. Well, what if we bump it up to, instead of 30, 40 grams of sodium chloride? Well, you'd have to look that up, but at that point, we get sludge. Okay, so this is an example of a saturated solution. The B, the second one is saturated. The first one is unsaturated. Now, this is actually a bunch of different compounds, a bunch of different salts. So if we find sodium chloride here, is sodium chloride here? No. See, potassium chloride. But what this is doing is it's saying how soluble is that particular compound at these temperatures. So most of them have what we call kind of a positive slope. It's like with sugar. You would probably tell me, well, if I wanted my sludge to go away, I just put it on the stove. And the solubility of sugar increases. And you're right. A few of them have a negative slope, like this cesium sulfate. Okay, that means as you increase the temperature, the solubility goes down. What's along the y-axis is how many grams of that salt you can shove into 100 milliliters of water at that temperature. So solubility. Right. So supersaturated. Now, actually, sodium acetate. Sodium acetate is what I have in something I'm going to show you here in a minute. Now, this actually is a, you can't tell, but it looks like a little petri dish. Okay, it's in a watch glass probably. It has some supersaturated solution of sodium acetate in it. So what you can do is with supersaturated solution, super anything, it's pretty, tenuous. It wants to relieve itself of being super. So what they're doing, I think, is what we call seeding. So just putting a sodium chloride crystal in there. And what happens is the sodium acetate, which was supersaturated, hanging out in solution that it really shouldn't have been in, it starts coming out of solution, starts forming that sludge. It starts precipitating, crystallizing, whatever you want to call it. So kind of from left to right, this is the same material. All they did was to kind of stimulate it. So here I've got, and one of the things I'm going to talk about last on this part is this idea that some processes release energy, which makes a great hot pack, and that's what I've got here for you here today. And then actually some processes take in energy. We call, if it releases energy, exothermic, exiting, okay? And if it's taking in energy, we call endothermic, it's taking in energy. So they make great cold packs, but this makes a great hot pack. So I'll want these back, but these I'm pretty sure are sodium acetate. And I do some dabbling with my telescope, and I've done it in very cold weather before, and my husband's kind of got these with that in mind, okay? So when you get them, instead of seeding them, like S-E-E-D, seeding them, what you're going to do is you're going to agitate it by, there's like a little, sort of little flexy thing in there. Go ahead and flex that to see if you can make the sodium acetate come out of its supersaturated condition. I want to work better sometimes. That's what I'm going to do. It just did not work. Did you look at it? Oh, no. Is it? I really did it. It's happening. Oh, God. This is so cool. How much you can you go through? Yeah, because it's cold. Yeah, it's cold. How do you go back to normal? The instructions that come with it say to get it back to supersaturated, you just have to boil it for like a minute. And it'll go back and say, this is reusable. This is exothermic. Isn't that cool? I have a video to kind of show you the coming out. So here are some videos that I snagged from my here's some videos I snagged from my Gen Chem Friday. Thank you for reminding me. This will be due on Monday. Good catch. Very good. We'll go ahead and take a look at the next part. Parts is parts. So I just want to get a few slides down the road to kind of make sure we're all on the same page. We talked a lot about, we talked about elements, we talked about atoms and how atoms join together to make compounds, two types of compounds, molecular compounds and ionic compounds. Now I want to talk about this idea of when compounds or elements come together and react, okay? One of the things I appreciate about science is some of its conciseness. I'm not a wordy person. Our daughter's taking English comp right now, and she's doing great. When I took English comp, I'm like, just barely got by, okay? But anyway, so I like how we represent chemical reactions with what chemical equations. So it looks like I hid the word new substances. So we know that a reaction has happened if we get something new formed, okay? Now, one of the things in this class is that it's not like magic. You can't like make new elements. Like you can't start with hydrogen and end up with helium. If you start with hydrogen, you're going to end up with hydrogen. In fact, what we're going to do on Monday is we're going to kind of talk about how you make sure that you have the same atoms that you start with are the atoms that you end with. Okay? But just in general, know that. And when it says that, so new substances are formed because it's kind of what we talked about with regard to compounds being formed, is we said that atoms stick together with regard to electrons. Either an electron is transferred and you get a cation anion and then it's an ionic bond, or electrons are shared and you have a covalent bond. So what's happening kind of behind the scenes to make our new substances is that electrons are doing their thing. So we write, we're going to talk a fair bit, and in tomorrow's lab that hopefully we get to do, I think it's 5 chemical reactions. You guys will do 5 chemical reactions. Nothing that you can eat. You know, sometimes I hear students take chemistry and other places and they can make things they can eat. We're not doing that. But you'll be doing 5 chemical reactions, and they will be represented by chemical equations. So I think you've probably kind of seen chemical equations before. We read chemical equations from left to right in general, kind of like we read sentences. The thing we start with are the reactants, and the thing we end with are the products. Reactants are kind of like our ingredients. Products are the products, the things that's produced. Okay, so in general, we put the reactants on the left and the products on the right, just like we do. Usually we use line to identify that. Oh, I know what this is. Formulas. We usually use formulas, chemical formulas. So in other words, instead of writing out water, we'll use H2O. And like I said, it's more of a picture. And all those words, blah, blah, blah. So I have this little video. It's about 10 minutes or so. But it's supposed to be, and it is some kind of cool chemical reactions. So let's do this slide right quick, though. How do you know chemical reaction has occurred? How do you know new substances are formed? Well, sometimes you'll have a change in color. Sometimes you'll have the precipitate formed, kind of like in the video we saw showing you saturated solutions. Sometimes you'll have a gas formed. Sometimes it will emit light or heat. So this one says actually the emission or absorption of heat. So what do you guys think about those? Did it emit or absorb heat? Emitted heat, yeah. Emitted heat. Okay, so let's take a look at this video. Scale recipe up and down. You can also do that with a balanced chemical equation. So in tomorrow's lab, which hopefully you get to do, you'll be doing, I think it's 5 chemical reactions. And you'll see these little letters next to the reactants and products. So S stands for solid. I'll get you started. So what do you think L stands for? Liquid. How about G? Gas. Perfect. And AQ, like it says at the bottom, means aqueous. And then in some of the videos we watched, there were certain reacting conditions, like the thermite. Looked like it needed flame, okay, to start it. Sometimes some chemical reactions need certain conditions, like flame or heat. Sometimes you need a specific temperature. Sometimes you need a catalyst. We heard in the video they talked about a catalyst with elephant toothpaste. So all a catalyst does is help a reaction rate occur more quickly. And catalysts aren't consumed, so that's kind of nice. Some reactions need it to be perfectly done in order for them to happen. So, very cool. Well, that's as far as I wanted to get today, so if it's okay with you, out a few minutes early, and that's a good starting place for Monday. Yep. And so, I think we're going to, did they cool it? Did they? Yeah, it's still a little warm. I'll go boil them and do it next time.